Hello everybody, this is Dr. Christopher White and welcome back to part 3 of Rocks Part 1. As you can see, we've left the igneous rocks now and we're moving on to metamorphic. Alright, let's get going. So, metamorphic rocks are the result of mineralogical changes caused by increases or decreases in pressure and temperature. So the changes in pressure and temperature cause minerals to become unstable. So every mineral has a temperature and pressure range in which it's happy. Once you leave that range, the mineral will naturally become unstable, and so it will break down, forming a new mineral. Now, the key thing about metamorphic rocks is at no point do the rocks melt. So obviously once you start melting the rock, you're moving over into the igneous regime. So we can't have metamorphic rocks melting, and that works for 99% of cases. So when we classify metamorphic rocks, we classify them based on the mineral assemblage that we see and the textures that we see in the rock. So we don't, so there's a couple of things that are working together to allow us to classify the rock. Okay, so the precursor lithology, so the thing that's being metamorphosed, is referred to as the protolith. So the metamorphic rocks that you produce, the metamorphic rock that you produce is a reflection of that protolith. So the chemical composition of the protolith is obviously going to affect the chemical composition of the metamorphic rock you produce. So if your metamorphic rock is, if the protolith is very, very rich in, let's say, calcium silicate minerals, well, obviously the metamorphic rock you produce is also going to be quite rich in calcium silicate minerals. It's not suddenly going to become very, very rich in iron silicate minerals because there's no iron in the original protolith. So you can't just create something out of nothing. So typically, the metamorphic rock you get is a reflection of the protolith. Now, when we discuss metamorphic rocks, we typically only discuss basalts and muddy sedimentary protoliths. Now, the reason for that is those two types of rock, when you metamorphose them, they produce nice, clear changes in metamorphic minerals as the pressure and temperature increase. This means we can track what's happening to the rock quite easily. In contrast, if we were to take something like a piece of granite and we start increasing the pressure and temperature, well, the granite just sits there, does nothing. And we've got to keep ramping that pressure and temperature higher and higher and higher. And the granite won't metamorphose at all until you reach very high temperatures and quite high pressures. So that's why we only tend to focus on the basalts and the muddy sedimentary protoliths, because they give us the nice changes in metamorphic minerals that we're looking for. So when we discuss metamorphic rocks, we are going to discuss index minerals. So an index mineral is a distinctive mineral which will only occur under a certain pressure and temperature. So when we look at a metamorphic rock, we will look for those index minerals, and if we find them, then that will tell us what pressure and temperature our metamorphic rock has been exposed to. So they're actually extremely helpful. Now, not all minerals will be index minerals. Something like quartz or feldspar, well, they're in nearly every single metamorphic rock out there. So when it really comes down to it, they're completely useless. When it comes as index minerals, they can, they're present under a whole range of temperatures and pressures, and a whole different variety of protoliths. So they're not going to tell us anything. On the other hand, something like kyanite, for instance, which is a lovely index mineral, is only present under very certain conditions. So, for instance, in the case of kyanite, you need very, very high pressures but low temperatures. And so as soon as you see kyanite, you know the conditions to which your metamorphic rock has been exposed. So the thing about these index minerals is as soon as you exceed the stable range, so the temperature and pressure range for that index mineral, it breaks down and it's gone, and it will turn into a new mineral. Now, this is very, very useful to geologists, because what we can do then is we can use those index minerals to define things which we call facies. And a facies is simply a pressure and temperature range in which certain a certain mineral or minerals will appear in a rock. And as soon as you leave that pressure and temperature range, you've left that facies, because those index minerals will break down and disappear. Now, the facies classification diagram we use, which is on the next slide, is based on the metamorphism of a basalt protolith. Okay. Now, one final thing: each boundary of this facies diagram is based on the loss of one or more index minerals and the appearance of a new index mineral. Okay, so this is the facies diagram right here. So you can see on the lower axis here, on the x-axis, we have temperature, and on the y-axis we have pressure. Obviously, temperature is increasing to the right, and pressure is increasing to the top. So what can we see? Well, first of all, this field is blank because you don't achieve those conditions under realistic settings. So that field is left, there's nothing going on there. Now, you can see that we have certain types of metamorphism that are occurring at lower temperatures and pressures. I'm going to be honest, we're going to avoid those lower temperature metamorphic rocks. We're going to focus on these slightly higher temperature facies. So we've got the green schist facies here. Now, green schist facies rocks have chlorite, epidote, and actinolite in them. Those are your 3 index minerals. And because they're all strongly green minerals, they will give the rock a very strong green colour. So if we can find those 3 minerals in our metamorphic rock, we know we have to be in green schist facies. Now, if we were to increase the pressure and temperature outside the range of green schist facies, so these lines are showing me the temperature and pressure range for green schist facies, so green schist between about, let's call it 275 and about 475 Celsius, and in terms of pressure, between about 1 and 8 kilobars. So if you take a basalt and you metamorphose it, so anywhere within this field, those temperature and pressure conditions, the minerals are going to, and so you're going to see the appearance of the index minerals chlorite, actinolite, and epidote. Now, as soon as we leave this field of stability, so let's say we go from green schist into amphibolite over here, what happens is the chlorite, actinolite, and epidote break down, and instead they're replaced by large quantities of hornblende, plagioclase feldspar, and garnet. So we lose one set of index minerals here, and we gain a new set of index minerals here. So this is the power of index minerals. As long, if we can see them in the rock, it helps us work out to what pressure and temperature a rock has been exposed, and we also can use them to define these facies fields. Okay, so typically when a geologist is talking about metamorphic rocks, they don't give temperatures and pressures. They'll simply say, right, well, this rock achieved green schist facies or blue schist facies or granulite facies. Okay, the reason for that is in order to actually come up with a temperature and pressure for a metamorphic rock, it actually takes quite a bit of work. You have to use geothermometry and geobarometry to do that, and that requires you to have the correct minerals. It requires you to take lots and lots of data, and it also requires you to have the money to be able to use the equipment to do it. So most of the time you can't actually produce a temperature and pressure for your metamorphic rock. So all you can do is you can look at the index minerals and you can say, right, well, my metamorphic rock clearly falls somewhere in the green schist facies field because I can see the chlorite, the actinolite, and the epidote. So when we're discussing metamorphic rocks over the next few slides, we are going to be discussing eclogites, blue schists, green schists, hornfelses, amphibolites, granulites, and a few others. Okay, and each of these different rock types has a distinct mineralogy, which will tell you, what field you're in. So you just have to look at the minerals, and it will tell you, right, which of the facies am I in? So what temperature and pressure range did my metamorphic rock form in? Okay, so as I said, this diagram here is based on the metamorphism of a basalt. Okay, so all these fields here are defined by what happens when you metamorphose a basalt. But as I also said in the slide before that, we also like to talk about mudstones, so muddy sedimentary rocks and the metamorphism of those. So what you'll see here is you'll see a very simplified diagram which has green schist facies, amphibolite facies, and granulite facies. Green schist, amphibolite, granulite. And this is showing you the changes in mineralogy which we see as we move from one facies to another. So in the green schist facies, we look for the index minerals chlorite, epidote, and actinolite. Amphibole, by the way, includes minerals like actinolite and hornblende. So we look for these three index minerals when we're looking at when we're trying to discern a green schist facies rock. Now, as soon as we leave the green schist facies field, chlorite very quickly becomes unstable and is lost. Epidote persists for a while but is eventually lost. The actinolite will change into a new amphibole which is called hornblende. So actinolite has a green colour to it. Hornblende is black. So there's a very visible change in the colour of the rock. We will also see the appearance of garnet. If you increase the temperature even further, we will eventually leave amphibolite facies and will end up in granulite facies. In this case, amphibole suddenly finds itself becoming unstable, and it will then be replaced by pyroxene. So simply by looking for the index minerals, we can work out the general conditions to which our rock has been exposed. Now remember, this is for a basalt up here, this top diagram. This bottom one is for a mudstone, so a muddy sedimentary rock. So obviously, because the protolith has a different composition, the minerals you get are going to be different. So what do we see? Well, the first thing to remember is quartz and feldspar. Well, they are ubiquitous minerals. They're all over the place, and in terms of being an index mineral, they're pretty useless. So we're not going to concern ourselves with quartz and feldspar. So the first thing you'll notice is we have the same facies, green schist facies here, amphibolite facies here, granulite facies here. You will, however, notice that the types of rock which we're forming are now different. So up here we formed green schists, amphibolites, and granulites, because remember, we're metamorphosing a basalt. Down here we're metamorphosing a muddy sedimentary rock. So instead we're going to form different rocks with different minerals and different textures. So in this case, we're actually going to form a couple of different types of rock down here called a slate or a phyllite. As we increase the pressure and temperature, they'll change into a schist. And as we increase the pressure and temperature, the schist will eventually turn into a rock called a gneiss. Now, these are terms I'm sure you've heard before in your earlier class. So, once again, different protolith composition will produce different minerals. So we see we have chlorite, but we don't have epidote and actinolite anymore. Instead, these lower grade metamorphic rocks formed from mudstones will be dominated by chlorite, muscovite, and biotite. Now, as we start to increase the pressure and temperature, the chlorite you can see becomes unstable and is lost. Muscovite persists, biotite persists, and we have the appearance of garnet, a mineral called staurolite, and under the correct conditions, a mineral called kyanite. Now, the presence of kyanite, staurolite, and garnet will tell us we are now in the intermediate, so the amphibolite facies field. As we move from the amphibolite facies conditions into the granulite facies conditions, we lose kyanite and staurolite if they're present, and they're replaced by a mineral called sillimanite. We will also eventually lose biotite and garnet as well. And so what you can see is we have these very distinct changes in index minerals. So that once again, though, they're telling us about the temperature and pressure conditions to which our rock is being exposed. And this is what we look for when we're looking at metamorphic rocks. I am just going to drive this point home one more time. When we discuss metamorphic rocks, we are normally always just discussing the metamorphism of basalts and the metamorphism of mudstones, so muddy sedimentary rocks. Okay, so when we try and metamorphose our rocks, we can take one of three distinct paths. We can take the contact path, which is here in pink, the regional metamorphism path, here in green, or the subduction path, here in blue. Now the conditions for each of these paths are different. So you'll see down here the contact metamorphism path, well, it's quite low pressure, but it's very high temperature. So contact metamorphism, low pressure, high temperature. Subduction metamorphism, you can see the temperature is relatively low. Okay, we're at this side of the diagram. So low temperatures, but the pressures, well, they're very high. So subduction metamorphism will occur in environments where you have very high pressures and low temperatures. And then we have regional metamorphism, also sometimes referred to as Barrovian metamorphism. And in this instance, you can see we have a steady increase in both pressure and temperature. Now, when we discuss regional metamorphism, we typically define it as high pressure, high temperature. So, contact metamorphism, low pressure, high temperature. Regional metamorphism, high pressure, high temperature. Subduction metamorphism, high pressure, low temperature. And obviously, as we change the conditions, so as we increase the pressure and temperature, obviously our rock is going to pass through one facies and go into another. So we're going to see these changes in the index mineral as our rock moves between the facies fields. Okay, so metamorphism can occur in two discrete directions. There's prograde metamorphism and retrograde metamorphism. So prograde metamorphism is when you increase the pressure and or temperature. So essentially it's called prograde because you're kind of driving the metamorphism forward by increasing that pressure and temperature. Retrograde metamorphism is when you decrease the pressure and temperature. So normally when we think about metamorphism, we just consider the prograde part. You know, the pressure and temperature gets higher and that drives the changes in the mineralogy. However, it obviously works the other way. You can also leave the stability field for a certain index mineral by making the pressure and temperature lower. And once again, as soon as you leave that stability field for that index mineral, it's going to change into a new mineral. Doesn't matter if you increase the pressure and temperature or you decreased it, you're still driving that change. So always bear in mind metamorphism occurs in two ways, prograde or retrograde. So regional and subduction metamorphism, I should say, and subduction metamorphism are formed in environments with moderate to high pressure. That's a terrible sentence, I don't know what I was doing there. So when we are discussing regional metamorphism and subduction metamorphism, they are occurring in higher pressure conditions. Now, what this means is because there's all this pressure on the rock, the minerals in the rock will grow with a certain orientation. Okay? So if you imagine we're taking a piece of rock and we are squishing it from the top and the bottom. Okay, so that's where the pressure's coming from, top and bottom. So we're pushing down it, we're squishing the rock. Well, that means that the minerals which form during metamorphism are being exposed to that pressure. And they will preferentially align themselves at 90 degrees to the direction in which the rock is being compressed. So if I'm compressing my piece of rock north-south, the minerals are going to align themselves east-west. Now this alignment of the minerals can produce something which is referred to as a foliation, and this is when we see a distinct layering in our metamorphic rock, and that's one of the things that we look for when trying to classify metamorphic rocks. We not only look at the mineralogy, we also look at the textures. Is there a foliation present? Are the minerals aligned? Contact metamorphism, on the other hand, occurs in low pressure conditions. This means there's no force which is trying to make the minerals align. This means you don't get a foliation, so contact metamorphic rocks will be unfoliated. So the presence of this foliation tells us if the rock has been exposed to higher pressures, in which case we'll get a foliation, or lower pressures, in which case we will get an unfoliated metamorphic rock. Now, you can also get unfoliated metamorphic rocks under very high pressures. So if we just go back here for a second, here we have eclogites right at the top there. So very, very high pressures and very, very high temperatures. Now in that situation, they're forming in the mantle. And in the mantle, the pressure is equal in all directions. So that essentially means because the pressure is equal in all directions, the minerals can't align. Okay, so let's start off with contact metamorphism. So contact metamorphism is simply the result of the country rock being heated up by an intrusion. So some magma intrudes the crust and it heats up the rock that it's in contact with. Not really a huge shock. So intrusions will tend to form, geologically speaking, in areas where we have relatively low pressure. So they tend to form higher up in the crust. So the pressure, geologically speaking, is quite low. Obviously, though, because the rocks are in direct contact with a magma, which is very, very hot, well, clearly the temperature is going to be quite high. So contact metamorphic rocks, high temperature, low pressure. Now, what happens is obviously the temperature is going to be higher for the rocks right next to the intrusion, and the temperature is going to steadily decrease as you move away from the intrusion. Basic common sense. Now, once again, that means we have a steady change in temperature, and that's going to drive a change in the minerals that we see. So obviously the rock which is right next to the granite is going to be exposed to the highest temperatures, so we're going to see higher temperature metamorphic minerals. As you move away from it, we're going to see the metamorphic minerals get steadily lower and lower temperature, well, should I say, we're going to see a decrease in temperature, and so we're going to get lower and lower grade metamorphic minerals. So we're going to have really high grade metamorphic minerals over here because it's very, very hot. And as we move away, the metamorphic grade is going to steadily get lower. And so over here, we're going to see quite low grade metamorphic minerals like muscovite and chlorite. Whilst as we move closer to our intrusion, we're going to start seeing higher temperature minerals like cordierite and sillimanite appearing. Now, the great thing is because we see this change in the mineralogy as we move away from the intrusion, it means we can use the minerals to define certain bands. Okay, so these bands are referred to as aureoles, and in this diagram you can see them right here. So now this is for the metamorphism, once again, of a muddy sedimentary rock, okay, a shale and a sandy shell. And so what we're seeing is the muddy sedimentary rocks being metamorphosed. Obviously, when they're metamorphosed to quite low temperatures, you get the muscovite and chlorite forming. As the temperature gets high, you go to biotite and andalusite, you lose the muscovite and chlorite. As you get even closer, the biotite and andalusite become unstable. They get replaced by cordierite and sillimanite. And then if you come even further, you'll actually end up with a type of rock which is called a hornfels. So we'll worry about that particular term in a bit. Okay. So the metamorphic grade, okay, so that's the temperature at which the mineral is stable, is increasing towards the intrusion. So the grade increases towards the intrusion because the temperature is increasing. So that means we have high grade metamorphic minerals here, so they're stable at high temperatures. And over here we're going to have low grade metamorphic minerals over here because they're stable at lower temperatures. So as the pressure is low, we're not going to get a metamorphic fabric because there's nothing making those minerals align themselves. And so this means we end up with a very distinctive type of rock which is referred to as a hornfels. So hornfelses will typically form from the metamorphism of muddy sedimentary rocks. Okay, and you can also get them forming from basalts as well. The situation isn't quite as clear cut. So when we are talking about hornfelses, we typically look at the lower portion of the diagram down here. So there's the hornfels field. Now what I'm about to show you is this diagram flipped on its head. So we're going to have low temperatures we're going to have low pressures up here and high pressures down here. So here we go. So this is the eclogite field down here, which was at the top of the previous diagram. Now it's at the bottom, and we can see here is the hornfels field. And so we go albite epidote hornfels, hornblende hornfels, pyroxene hornfels, and then as we increase the temperature even further, we end up with a type of rock called a sanandite. And so this is what we see when we contact metamorphose a basaltic protolith. So at lower temperatures, we'll get an albite epidote assembly. So we'll see the mineral albite and the mineral epidote in the rock. As we increase the temperature even further, they will become unstable and they will be replaced by the index mineral hornblende. increase the pressure increase the temperature even further. The hornblende becomes unstable. We then see the appearance of pyroxene, and then increase the pressure and the temperature even further. We end up with a type of rock called a sandandite. So once again, just like we were seeing here, as you move towards the intrusion, you get a distinct change in the mineralogy that you see, and that allows you to define these aureoles, these bands that contain, certain minerals. So if you saw in the previous diagram, sandstone and limestone undergo textural changes. So what we have here is we have a layer of limestone. So your limestone turns into a marble. Limestone consists of calcium carbonate. Marble consists of calcium carbonate. Okay, because once again, the rock you produce through metamorphism is a reflection of the protolith. The same goes for the sandstone down here, dominated by quartz. So the sandstone down here is going to be metamorphosed, and that's going to form a very quartz-rich metamorphic rock called a quartzite. So the types of metamorphic rocks we're getting in their mineralogy are a direct reflection of the protolith. So you'll notice that neither the limestone or the sandstone shows these very, very distinct changes in mineralogy because they are such stable rocks. This sandstone is made of nothing but quartz. Okay, if you start heating up a sandstone, it just sits there. Nothing happens to it. It only begins to change into a quartzite when the temperature starts getting really, really high. Okay, so just bear that in mind as well. Now, as we discussed, mudstones produce a very distinctive sequence, just like the basalt will as well. One final thing we need to remember is, well, why do we get these contact metamorphic aureoles at quite low pressures? So here's a situation. So this is the crust here, so top 25 kilometers of the Earth's crust. You'll notice that this intrusion down here does not have a contact metamorphic aureole around it, so you don't see these bands. The reason for that is the temperature down here is quite high. So the temperature in this area is going to be between 300 and 700 Celsius, let's say. So that means when the magma comes in, let's say the magma's got a temperature of 700 Celsius, it's trying to heat up a rock which is 700 Celsius. So it doesn't do anything. It's just, doesn't change the rock at all. It's only when you get to higher levels in the crust and the rock is at much colder temperatures, then all of a sudden when you apply a intrusion to it, which is going to push heat into the surrounding rock, that's when you're going to start causing the metamorphic rock to change via contact metamorphism. So now we need to think about regional and subduction metamorphism. So regional and subduction metamorphism are caused by the large-scale action of heat and pressure. Okay, so both of these types of metamorphism are associated with convergent plate boundaries, where you have pieces of crust coming towards each other. Okay, and those will result in the formation of mountain ranges. So regional and subduction metamorphism is the result of orogenic processes, so the collision between continents. The metamorphic grade increases towards the core and base of the crustal thickening. So when you actually have a mountain range forming, the crust gets very, very thick. Okay, because you've got a collision. This is acting like a crumple zone. The crust is literally crumpling to accommodate the impact of this piece of crust here banging into this piece of crust right here. And so what happens is the crust here begins to thicken up. So in terms of regional metamorphism, which is going to occur in the mountain range itself, we obviously see the higher grade regional metamorphic rocks down towards the bottom, where pressure and temperature is highest. And we steadily see the metamorphic grade decreasing as we come up for our mountain range because the pressure and temperature is going down. Now, in terms of blue schist facies and eclogite facies, they're associated with pieces of oceanic crust which are being subducted. Now, we're going to, there are actually some very, very distinct conditions which have to be met to form these two types of metamorphic rock, and we're going to discuss those in a second. Okay, so let's think about regional metamorphism first of all. So we've gone and formed a nice mountain range. So here it is. Okay, so here's our mountain range, and of course on the underside we have to have a mountain root because we have to balance out the mountain range. Okay, so we have to have, obviously, this mountain range is sitting much higher than the surrounding land. That means if you didn't have this root down here, it wouldn't be balanced, so the mountain range would literally start to fall over. Okay, this doesn't happen though because we have the counterweight of the mountain root down here at the bottom. So that's why you have this thickening of the crust. So regional metamorphism, say, occurs within mountain ranges. So what we'll notice is as we come down and get deeper and deeper into our mountain range, obviously the pressure and temperature is getting higher. This means as we go down, we are going to see distinct changes in the metamorphic rocks because of those changes in pressure and temperature. And so what we'll see is we'll see the appearance of certain key minerals, these index minerals, as we go down. So obviously up here in the lower pressure and temperature ranges, we're going to see metamorphic rocks which contain chlorite. Increase the pressure and temperature even further, chlorite's going to disappear, we're going to see biotite. The biotite is eventually going to become unstable, garnet's going to appear. Garnet will eventually become unstable, we'll see andalusite appear. Andalusite will become unstable, sillimanite will appear. So once again, we can use these distinct, these index minerals to work out what's happening to our rock. If we start seeing metamorphic rocks which contain sillimanite, well, we know those, if we know those rocks have been regionally metamorphosed, we know they must have formed quite deep within the mountain range under quite high pressures and temperatures. So as you can see, we get these nice distinct bands forming within our mountain ranges. Now the problem is eventually mountain ranges stop forming. So then what's going to happen is the mountains up here are going to be eroded away. And so this is going to cause the mountain root up here to pop up, because as the mountain is, mountains are removed over here, so as you remove the mass of the mountains there, the mountain root down here will naturally come up. And so this means we get a situation like this. So once the mountain ranges are removed, we get this crustal rebound, the mountain root moves upwards and it pushes these metamorphic bands up to the surface. And so we end up with a situation like this. So this is our sillimanite band here, this is our very, very high pressure, high temperature band here. And this is our chlorite band here and here. This is our lower pressure, lower temperature band, or lowest pressure, lowest temperature band. And so what you'll notice now are these bands are exposed on the surface of the Earth. So we can see these metamorphic zones. So if we look at a real life example, here we go. So let's look over here. So this is Nova Scotia in Canada. Okay, so you can see this box here shows you what we're looking at. We're looking at the end of the island here. And so what can we see? Well, in green here we have chlorites. In green we have biotites. In light blue we have garnet bearing rocks. In dark blue we have andalusite bearing rocks. And in purple we have sillimanite bearing rocks. Chlorite, biotite, garnet, andalusite, sillimanite. What we're looking at here is we're looking at a sequence of rocks which is telling us we're going from quite shallow levels in a mountain range to quite deep levels in a mountain range. So this tells us this end of Nova Scotia was once part of a mountain range, and we can see this was where the core was located, and we are steadily moving away from that core. We see the same thing over here. So this is in the New England area. So we've got Vermont over here, got New Hampshire over here, and what can you see? Well, once again, we have where we go. We're going to go for the high grade rocks. Well, we have lots of intrusions to begin with. That's the what am I saying? Ignore me, please. So these red spots here represent quite high temperature metamorphic rocks. There's the presence of sillimanite telling us it's a very high temperature metamorphic rock. We then have slightly lower temperature metamorphic rocks. Sillimanite is still there, marked in orange. Then we have amphibolite facies rocks appearing. They give way to another type of amphibolite facies rock, which is marked out in green. Then we have another amphibolite facies rock in the kind of minty green. Then we are into a low-grade amphibolite facies rock here in the neon blue. And then eventually we get out to green schist facies here in pink. So once again, what we're seeing is a transition from high temperature metamorphic facies here to low temperature metamorphic facies here. And once again, we're going from the center of a mountain range running down here, and we're moving away from that mountain range. So once again, here's the center of our mountain range here, and the metamorphic grade is decreasing as we move away from it. That's exactly what we can see right here. Metamorphic grade gets lower in this direction and in this direction. So once again, we can see, that once upon a time there used to be a mountain range here. The area has been, eroded relatively flat. The mountain range is gone. It, probably went hundreds of millions of years ago, but we can still see the metamorphic signature of that mountain range having been there. And the same thing will happen with modern mountain ranges. So let's say the Andes or the Himalayas. At the moment, in the core of the Andes, for instance, we are going to have these very, very high pressure, high temperature metamorphic rocks forming. Eventually, though, the Andes, the formation of the Andes will stop. They will be eroded away. The crust will bounce up, and these metamorphic zones will be exposed. And along the western side of South America, you will have a situation like this, where you will be able to see that once upon a time there used to be a mountain range there. Okay, this is a great place to stop. So, once again, stop the video, get up, have a walk around, get a glass of water, have 5 or 10 minutes away, let your, straighten your head out, and then come back for part 4, please.